Hi, it's Mrs. Pope, and today we're going to talk about using exponential and log functions. Our goal is to use logs to solve exponential growth and decay problems, and I've given you two examples of what the typical growth and decay problem graph looks like. So here we have continuous exponential growth, and the way I know it's continuous is because of this E, which we'll talk about a little bit later. But E is the value that in the financial world they use to calculate continuous growth. So this is the general shape. As we read left to right, it goes up. The x-axis acts as an asymptote. It never touches the x-axis, and it always goes through 0, 1. And our continuous exponential decay, notice it goes down as we read left to right. It gets closer and closer and closer to 0, but never touches it. Goes through 0, 1, and its equation is y equals a times e to the negative kt. A is the initial value. That's what you start with. K is the constant rate that it's either growing or decaying, and T is the time in years. So something like exponential growth, we're going to talk about money. You put money into a savings account, it grows. Something like decay, maybe in a petri dish, if you've done that in science, how you see bacteria decays, or we're going to look at the half-life of carbon-14 in a little bit as an example. So exponential growth, always growing super fast. This exponential growth and decay is the fastest rate of change that we're going to see this year. So hold on tight, it's pretty exciting. All right, example 1, continuous compound interest. Here's a real world exponential growth problem. So our formula, A is equal to PERT. If you notice, it is exactly the same, it looks the same as the one that I gave from the graph. These are just the variables that they use in the financial world. A is equal to the amount in the account. P is equal to the initial principal, how much you put in the account. R is the interest rate as a decimal. And T is the time in years. So let's say that Gabriella's grandparents deposited $3,000 into a college savings account when she was born. That's nice of them, right? They got 4% interest, and it was compounded continuously. Continuous is why we have to use E in our equation. E represents a number that will help the financial world or people in the financial market to calculate continuous interest. Otherwise, you can have daily interest, you can have weekly interest, you can have monthly interest. That's how often they give you the interest you earn on your money. Your money is always growing. It's continually getting the interest. So let's see what's going to happen with Gabriella's account. How much will she have in 10 years? So in 10 years, take a guess. What do you think? Write something down really quick. Just guess. Okay, now let's see if you're right. Or even, close. A is equal to 3,000 using our formula times e to the power of 0.04 times 10 years. So A is equal to 3,000 e to the 0.4. If you calculated it, did you get something close to $4,475.47? Did anybody guess that exactly? All right, so in about 10 years, her 3,000 is going to grow to about 4,400. Not terrible. So how long will it take her to reach 10,000? Maybe she's that's her goal for $10,000 for college. Let's see if she can reach it before she gets to college. So we want to know, for the amount in the account, we want it to be at least $10,000. So 10,000 has to be less than or equal to whatever it is we have in the account, which is 3,000 e to the 0.4 t. So we want to solve for t because we want to know how long is it going to take her. Well, in order to get t by itself, there's a few things we need to do. First, we're going to isolate the e. So let's divide everything by 3,000. Divide by 3,000. So we have 10 over 3 is less than e to the 0.4 t. Now we can use logs to get rid of that. So let's take the log of both sides. And I'm going to take the natural log so that the e goes away. So ln of 10/3 is less than ln of e to the 0.4 t. And we already know if we have ln of e, they cancel out because that's log base e. So ln of 10/3 is less than 0.4 t. Divide by 0.4. Divide by 0.4. All this can go in your calculator. And if you get it, you're going to get that the time is about 30 years. So it's going to take her about 30 years to get to $10,000. So either she needs to go to a school that's going to cost less than $10,000 or wait till she's 30 to go to college. That's probably not a good idea. So hopefully she gets some scholarships. All right, example 2. Here's our final example for today. Real-world exponential decay, half-life. You've probably dealt with this in science. The half-life of carbon-14 is 5,730 years. What half-life means is how long does it take to lose half of its atoms? So if it had 100 atoms, how long does it take to get to 50? Well, the half-life of, and go all the way down. The half-life of carbon-14 is 5,730 years. So that's going to stay around for a long time. So what rate is it decaying? We're going to assume that this rate is going to be pretty slow. Very, very slow. Well, here's the exponential decay formula, and let's plug in, let's see what we have. So A is our initial value, the initial value that we have. And then Y here is going to be, we're looking for the half-life. So we want to know when is it half of what it is. So we have whatever A is, we want half of that. That's what our Y, we want it to come out. When is it going to be at half? That's what we're trying to figure out. And our time is 5,730 years. All right, so let's see what we can do. We are trying to find, let's set it up, 0.5A is equal to, where are we? A e to the negative k times 5,730. All right, so here, notice we have our A's here. I have everything. I don't know what A is, but here's something neat. I can divide it out. I can divide both sides by A, and it's gone and doesn't even matter. So now I have 0.5 is equal to e to the negative k times 5,730. All right, so now let's take the natural log of both sides. ln of 0.5 is equal to ln of e to the negative 5730k. I just switched those around. And now that I have ln of e, that cancels out. So ln of 0.5 is equal to negative 5,730k. And if we divide both sides, k is going to be about 0.00012. Super small. And that makes sense because it takes 5,730 years for it to reach half of its time. So the rate at which it's decaying is 0.00012. So that's like 0.012%. Very, very slow. And the equation for, we asked also, what's the equation for the decay? So y is equal to a e to the negative 0.00012 t. There we go. Thanks for watching, and remember, you are responsible for your own learning.